So hey guys, this is Easy Peasy again and it's your boy MUSHRAF over here, and let's get started with the topic that is quantum wave function. And it is actually the most central part of the whole quantum mechanics. So we'll try to understand this in the most simple and understandable way actually. So before understanding what's a quantum wave function, we have to understand what's a wave function itself. So we'll be using some classical example. Suppose there is a particle which is oscillating back and forth in space with respect to time. So it generates kind of a wave, and this wave can be represented by a function, and this function tells us about all the states of the particle itself. Now what's a state? So a state can be a lot of things such as its position, speed, momentum, energy, probability. So what we are interested in is all the properties that we can acquire of the particle. Now that you have an idea about a wave function, it's time to proceed to quantum wave function. So quantum objects behave way different than the objects that we see around us. So it is impossible to use classical physics on these particles and understand its behavior. So we require a special branch of physics, that is quantum mechanics. So the reason we require quantum mechanics is because it is impossible for us to pinpoint the exact location of the particle in space. So what do? So when we are experimenting and we observe a quantum object, for example, now let's take an electron around the nucleus. So what we thought was the electron is orbiting the nucleus in some specific orbits, but it's actually not the case when we observe it. What we see is something like this. We see that the electron is like a cloud around the nucleus, and in some areas it appears to be dark, and in some regions it appears to be light. The region where it is dark, it signifies that the probability of finding the electron in that specific region is much higher than the probability of finding the electron in the region where it appears to be light. Okay, so we see that the electron itself is not moving in some specific orbit, and we cannot actually pinpoint its exact location. So it is much more like spread out. So this spread of electron cloud around the nucleus, what does it signify? Can we understand this? Well, to understand this, let's proceed to our next topic, that is particle in a box. The reason we are using this particle inside a box is to restrict the movement of the particle outside. Because when we usually study about the quantum objects, they are always inside some system interacting with other particles. So now let's take a box with some length L. And in the walls of this box are extremely hard so that no energy is lost when the particle is bouncing between them. So this is our x-axis, and this is also very important that we are only going to study about one axis and the particle is only allowed to move in the x-axis, so that we are able to understand this movement of the particle in a simpler way, because using three-dimensional space will only make it complicated. So let's start by one dimension, and there is a particle over here. For example, now let's take it's an electron, and when we put it in this box, the box is actually only a few nanometers wide, because obviously we're talking about quantum objects. So the particle starts moving on the x-axis backward and forward, and it somehow creates a wave. It may look like this, and to describe this wave we have a wavelength, that is lambda equals 2L by n. So in this case n is equal to 1. What if the n was equal to 2? So our wave would look something like this. What if n was equal to 3? It would look something like this. Now we finally have a wave which is created by electron. So this wave is nothing but matter wave. How do we describe this wave now? And now finally we have quantum wave function coming into picture. The example of particle inside a box, it is very clear that quantum objects produce matter waves. And to describe and explain this matter waves, we require a special function, that is quantum wave function. And the thing is, it tells us about the behavior of the matter waves. But the thing is, we don't really understand what it is. Well, why is that so? That is because across a lot of books it is said that quantum wave function does not have any direct physical significance. So what is this direct physical significance? To understand this, we have to understand what's a complex function, and you don't have to worry about it because even Schrodinger did not know what does it mean. So let's see. A complex function is something that is very hard to visualize, such as we are able to visualize everything around us, such as the position of particle, the speed and its momentum. But in the wave function, we are unable to visualize it, and that's why it is said that there is no direct physical significance. General way to represent a complex function is a plus ib, where a is nothing but a real function and ib is our imaginary function. So what is the difference? So this is what makes a lot of chaos over here right now. So what is I? I is nothing but under root of -1. There were a lot of scientists, like mathematicians, who did not know how to interpret this number. So they gave it a name that is imaginary number. So what is the difference between imaginary and real numbers? Real numbers, we come across like natural numbers, whole numbers, fractions, decimals, and this all can be plotted on a 3D space, that is a three-dimensional space where we have x, y and z axis. So all the real numbers can be represented in this space. But what about this? Well, we really can't explain this in real space. So it does not belong to the real numbers I. So how do we explain this function? So this is a space for real valued functions. And so we take that on this axis, real valued functions. And on this axis, we're going to take imaginary numbers and imaginary functions. This function lies between these two, somewhere over here. And that is the reason we are not able to visualize this function, that is wave function. So due to the lack of visualizing this quantum wave function, we say that it does not have a direct physical significance. Actually, it does exist, but we cannot visualize it, as we said. So what do we do now? What can we do? Well, this is a complex function and there can be a lot of different mathematical operations that we can use on this and bring this complex function to the real values. And this is nothing but the magic of mathematics, and let's see how can we do this. Let's come back to the topic particle inside a box, where we saw that the particle is moving inside this box and creating a matter wave, and what describes this matter wave is a wave function. And now let us say that this wave function is describing the probability of finding the electron in this region. So as we see that the amplitude over here is positive and amplitude over here is negative, and as we are seeing that this is nothing but our wave function that is showing the probability. So looking at this, we can say that the probability over here is positive and probability over here is negative, but probability can never be negative. So here comes our complex mathematics into picture, which helps us solve this problem. This is a complex quantum wave function which is represented by a plus ib, and it describes this wave, but it does not actually have a physical significance yet. So what do we do so that we get a real function or some real value out of this function? So what we do is we create a conjugate of this and we multiply this two, and what we get is something like a square plus, which in fact is a real valued function, and which will convert this wave into something like, okay, so over here again we get something like this, and we can see that there is no negative amplitude over here, so we are free with that and we have real valued functions. On the y-axis we have over here is number of probabilities, and here, as we know, is nothing but our x. And so basically what we did was we are calculating the probability density. So what we were trying to find over here was the probability of finding some electron, but Using this function, what we see is the number of probabilities. When we put a particle inside a box and we are only using this wave function, which is describing the probability of finding the particle somewhere inside a box, it is one thing is for sure, that the probability can never be zero, because the particle has to be existing somewhere inside the box. It cannot be outside the box. So the probability of finding the particle outside the box will be zero, but inside it can never be zero. So suppose I'm trying to find the particle in this area. So the probability is something 0.8. That means there are 80% chances of finding the electron in this position. And somewhere over here, it is only 0.2. That means 20% chances of finding it over here. But what happens when the number n increases? Over here we see that the probability is going negative, but there is nothing such as negative probability. So that's why we came up with this function, that is probability density. So now let's see what is it. So probability density will convert this function into something like this. And experimentally we do get real values for this function, which are actually useful in real life. We are trying to find the probability of finding the particle in this region, that is from A to B. So what we do is we integrate the region under this area. So we are going to integrate this function from A to B, that is this region. So this will give us some value C over here, and this value is our experimental value that we find for finding the probability of the particle in this region. So this is how we're going to use the probability density. So we should know the probability of finding the electron or the particle from this point to this point. Suppose we give it C and D. So if I change this to C to D, the probability will always be equal to 1, which is a very important condition to further solve the equation. So to finally conclude this video, all I can say is that the quantum wave function itself does not help us understand any physical significance, unless we operate it by some mathematical tools and get some real valued functions out of it. And using this real valued functions, we can find the real values, which can be used in real life. And surprisingly, when we do experiments, this value are in fact found out to be true. And in further videos, I'll be uploading more topics on quantum mechanics. So I hope you subscribe to my channel, like it, and it's your boy MUSHRAF over here, and it's easy peasy.